In this video, we're going to see an introduction to the quantum mechanical model of the atom based on Schrodinger and a few other scientists. We're going to take a look at the orbitals and their shapes and their characteristics before we jump into quantum numbers. So as a quick recap, remember we ended off by taking a look at Borethefer diagrams or Bohr's model of the atom, where we had quantized energy and the electrons were known to orbit on fixed tracks. And so, for example, an electron might exist at energy levels equal to 1, energy levels equal to 2, 3, 4, so on and so forth. And the strength of this model is that it was able to, first of all, incorporate quantization of energy. So electrons had quantized steps or energy levels rather than continuously losing energy and collapsing into the nucleus. And it was also able to explain the emission or the line spectrum of the hydrogen atom. So the idea behind this line spectrum is that when you would provide energy to the hydrogen in a gas tube, it would absorb energy, and then there'd be a release of energy that you could capture as an emission spectrum. And so these lines are the light energy that would be released by the hydrogen after it was energized. And scientists did not know how to explain that, but Bohr was able to explain it with his model. The idea behind this model is that Bohr would say that each of these lines comes from when there's an electron that receives energy, so you give it some energy. It then causes the electron to jump up an energy level up into a higher shell. And then as it goes down back to its regular energy level, it releases energy. And that's what is going to be one of those lines. So it releases energy in the form of a light wave. And so what Bohr was able to explain is that each of these different lines was basically a different jump that could happen. So, for example, if we look at the wavelengths here, let's take a look at these. So these numbers here are wavelengths. That tells you the corresponding wavelength of light that was released by the atom. So remember that if you have a long wavelength, you can represent that by the Greek letter lambda. A long wavelength will mean low energy. So this is a lower energy color of light that's spat out. And this over here, a shorter wavelength, means higher energy. So that was the higher energy that was spat out. And so how did Bohr explain this? Well, Bohr essentially said the higher energy one, so it's 410, for example, happens when an electron goes from energy level 6 down to energy level 2. That's a big jump. But let's say, for example, the 656 one, this one lowest in energy, would be when the electron goes from energy level 3 to energy level 2, so a smaller jump. And then these are kind of in between jumps, and they release smaller amounts of energy at wavelengths that are higher than than this one over here, for example. So Bohr was able to explain that emission spectrum quite well, but that was also its limitation. The limitation is that it only explains the line spectrum or the emission spectrum of hydrogen only, or of things that have one electron. So simple things. It couldn't explain the line spectrum for everything. So there was a bit of a problem there, and that means our model has to be modified. And just a quick reminder, I already explained it, but the line spectra, the lines tell you the difference in energy between the orbitals that the electron's jumping between. So another problem with Bohr's model is that scientists would sometimes ask, well, you can have an energy level over here, and over here, but why couldn't you have energy levels in between those? Like, why don't those steps exist? And Bohr couldn't really answer that with the way his model was drawn. He had the electron represented as a particle. And so to solve that, this scientist named Louis de Broglie comes along and says, I think it can solve that problem. I think I can explain why only certain energy levels exist. And the only way to really solve it is to think of electrons also like a wave. So electrons are said to exhibit a wave-like behavior. And so only certain waves can actually form. So for example, this wave forms, that wave forms, so there's this and this. But if you have something in between these, in these whole integer amounts, they won't form. So let's say I had an n is equal to, I don't know, 3.3. It might form like this. This is a bad drawing, but it might, overlap like that, and it won't match up at the ends here, so that just won't exist. So if you think of the electron like a wave, then that explains why you can only have n is equal to 1, 2, 3, 4, 5, so on and so forth, and nothing in between those. The other problem with Bohr's model is that it kind of lied or broke a rule. Bohr's model sort of implied that you knew exactly where the electron was, but we can't know that. That's Heisenberg's uncertainty principle. The idea behind that principle is you cannot predict with exact certainty the precise location or path. You can only really predict the probability of an electron being somewhere, and we usually say a 90% certainty. That's what that's how we define these models. So, and that's because the more you know about the location of electrons, the less you'll know about its momentum and path. So Bohr's model is not really following the uncertainty principle, and so we have to incorporate that somehow. So basically what we need to do is we need to say, okay, we need a new model that looks at electrons as waves, and that also incorporates probability rather than certainty. That's what Schrodinger comes to help us do. Schrodinger develops these fancy equations. You don't need to know them, but they're fancy equations called wave functions or wave equations. You plug in some numbers, which we'll learn about later on, and that gives you a graph. And these graphs are basically the probability distribution as to where you're more likely to find electrons 90% of the time. And then the origin is the nucleus in the middle there, in the nucleus. And darker regions represent higher chance of finding the electron closer to the nucleus. And then regions that are not as dark, well, that's a lower chance of finding the electrons there. But these graphs come from the wave functions, and they take into consideration probability, and also they take into consideration the fact that the electron acts like a wave as well, and not just a particle. So this is a wave function over here. We often represent the wave function like this, absolute value of the Greek letter psi squared. And it gives us these, again, 3D orientations, or these 3D graphs, these regions in space where electrons are likely to exist 90% of the time. And that's called an atomic orbital. So we no longer deal with orbits at this point. Now we're dealing with orbitals because we don't know the exact location of electrons. Thanks to de Broglie and Heisenberg, Schrodinger was able to create those fancy equations to give us a model of the atom that takes into consideration probability and wave nature of electrons, and no longer breaks Heisenberg's uncertainty principle, and that's the quantum mechanical model. So our electron's a particle and a wave, and electrons can exist in these probability regions in space that we call orbitals. And so we're going to learn a little bit about the orbitals right now. There's 4 different shapes or probability graphs you can get in terms of shapes. And they're given these letter names, S, P, D, and F. So you can have an S, P, D, or F orbital shape. So let's go take a look at what these look like. These are all the different orbitals here. We're going to take a look at what they mean, what they represent, and we're going to try to think about them in various ways so we can understand how that fits into the atom. So let's go to our s orbitals first. These s orbitals, if you look at them, their shape is spherical. So it's a spherical shape. The nucleus would be in the middle there, so there's no dark region there because there's no electrons there. And then the darker regions illustrate a higher likelihood of finding the electrons. But right now we can see it's a spherical shape. S doesn't actually stand for spherical. It is a spherical shape. S stands for sharp. It's these letters represent different harmonics that were studied back in physics. So you don't have to know the harmonic notation, just know S, P, D, F and know what their shape is. So spherical for the s orbital, And because the s orbital is shaped like a sphere, it's a ball, it's a symmetrical shape. So there's really only one sort of orientation or one shape around the nucleus. So there's only one possible orientation. It doesn't matter which way you turn the ball, it always looks the same. It doesn't matter how you put it on this 3D plane here. So there's always only one orientation or shape. Now, the thing with the s orbitals is that s orbitals can only hold a maximum of 2 electrons. So we're no longer really just placing electrons in these orbits. We're placing them in orbitals now. And so 2 electrons can be held in the s orbital. So let's go and take a look at the p orbital, and then we'll come back and rethink how we can view these to simplify it a bit. So here's our p orbitals now. P orbitals can exist in many different orientations because they're not spherical. They're actually more of a lobe shape, so you can describe them as lobes or dumbbells. And you'll notice that you can place them along the x-axis. So this would actually be called px. You can place them along the y-axis. That would be called py. And you can place them along the z-axis. That would be called pz. So there's 3 sort of different orientations you can have for the p orbitals: px, py, pz. But if you combine them together, this is what it looks like. So in reality, what a new term I need to introduce is this over here, a subshell. So let's consider this. We have a p subshell. You might also call it sub-level. Okay? And that p subshell is made up of 3 p orbitals. So think of it this way. This box here is a p subshell. And the box is divided up into 3 smaller boxes. Those are the p orbitals. So this would be the px over here, for example. This is 1. This would be the py over here. This is 2. And this would be the pz over here. So that's 3. So the p subshell always comes with 3 p orbitals. So they always come in a set of 3. So each orbital in the subshell can hold 2 electrons. This can hold 2 electrons, this can hold 2 electrons, and this can hold 2 electrons. Which means the entire p subshell can have a maximum of 6 electrons. Now we're going to start to represent electrons no longer as dots but as arrows. You'll learn why later on. But I'm just going to put in the electrons into the boxes as arrows. So here we have 2 electrons, here we have 2 electrons, and here we have 2 electrons. If we look at the s orbitals again, you can think of it the same way. You'll have an s subshell. However, the s subshell is the simplest one. It just exists as one s orbital. In other words, just one box, like this. Because it's a sphere, there's only one orientation, and that can hold a maximum of 2 electrons. The other idea I want you to get is that typically the S subshells have less energy than the P, and the P have less than D, and D less than F. So it's least is F, then P, then D, then F is the most. So the energy in the subshells will increase. Now there's exceptions there, of course, but that's the most part. That's the generalization. Now what I want you to get though is that the orbitals, so let's say you're looking at P subshell, and there's 3 P orbitals there, and you might ask, well, which orbital in here in the P subshell has the highest energy? They're actually all the same. So within a subshell, the orbitals that make it up are all the same in terms of energy. And we give it a fancy term, we call that degenerate. Degenerate. So the 3p orbitals in the p subshell are degenerate in terms of energy. The next shape to go over is the d subshell. So the d subshell is made up of several d orbitals. Because it's more complex, they're shaped like clovers or a double pacifier, we'll sometimes say, you have more possible orientations. This is an orientation, this is an orientation, so is this, so is this, so is this. So you have 5 boxes now. You have 5 d orbitals made of 5 d orbitals. So you have 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 corresponds to each one of these over here. Just like the p orbitals, each d orbital in the d subshell is degenerate, but they always come in a set of 5 instead of 3. And each of the orbitals, each of the boxes can hold a maximum of 2 electrons. And if there's 5 boxes, that means you can hold 10 electrons max in the d subshell. And I'm just going to draw in those electrons as my arrows here, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down, 1 up, 1 down. So that is a d subshell with 5 d orbitals. And that's the next one in energy. It's higher in energy than the p. Now we're going to go to the last type, which is called the f orbital. So we have an f subshell. And the f subshell is made up of a set of orbitals, of f orbitals. And you'll notice, this is it over here, there's 1, 2, 3, 4, 5, 6, 7. There's 7 f orbitals in an f subshell, and each of those boxes can hold 2 electrons. So that means they can hold a total of 14 electrons. So you can think of the f subshell like a big box here. One, 2, 3, 4, 5, 6, 7. And we can put our little electrons in, and that's 14 electrons that the f subshell can hold. And these are also degenerate to each other, these orbitals. And that's an f set. So this whole thing is the f subshell. And this is an f orbital, 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 an f orbital. Over here, this is the s subshell, and there's only one s orbital. That can hold 2 electrons max. This over here is the p subshell, and this has 3 orbitals. Orbital, orbital, orbital. This over here is the d subshell, and it has 5 orbitals. Orbital, 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 orbital. And each orbital can hold 2 electrons max. So here you can have 2 electrons max because there's only 1 orbital. Here you can have 6 electrons max because there's 3 orbitals. Here you can have 10 electrons max because there's 5 orbitals. And here you can have 14 electrons max because there's 7 orbitals there. So that's the idea behind the shapes, orbitals, and sublevels. Let's go see how that fits into the atoms using a visual. So we'll go and open up a visual over here. This is the orbitals visual. And so you'll remember that this was Bohr's idea, and we know it's wrong. We know you can't place electrons as dots. They don't exist in orbits anymore. They exist in orbitals. So this here is, let's just consider this our second shell in an atom. So this is shell number 2. Shell number 2 can further be divided into subshells or sublevels now. There's an S sublevel, and there's a P sublevel here. And each of the sublevels can be divided into orbitals. So the S sublevel is just, it's one S orbital. And then the P sublevel is the P orbitals. So P orbital here, here, and here. So in the second shell, you can have 2 electrons here, 2 electrons here somewhere, some region of space, some probability of being them in this region of space here. 2 electrons here and 2 electrons here. So that's 2, 2, 2, 2. That's 8 electrons in the second shell, similar to what you learned in Borethefer diagrams. A little bit more detail to add here. So this is a bit more information on the S sublevels. The big number in the front here indicates the main energy level. So this is energy level 1, S sublevel. So S sublevel at energy level 1, S sublevel at energy level 2, S sublevel at energy level 3. Notice that as you increase in the energy levels, you might be seeing an increase in the size of the subshell in the orbital. And that's because now you're getting farther away from the nucleus and you have other electrons in between, that shielding effect that's happening. So you're going to find electrons farther away from the nucleus when you increase your main energy level. But either way, regardless of what energy level you're in, whether the S is in the first, second, or third, or fourth energy level, it's only able to hold 2 electrons, like this box over here. Okay, and don't forget the middle is the nucleus. There are no electrons there. It's a spherical shape. Even though the S stands for sharp, we say it's a spherical shape. So here we have a model drawn of an atom that has a few electrons. This is its first shell. This is its second shell. What I want you to understand is that the S sublevel exists at all shells. 1, 2, 3, 4, 5. And regardless of where it is, it can only always hold 2 electrons. So in the first shell, we can just fit 2 electrons here. Now, once that's full, we go on to our next shell. And the next shell, we start placing the electrons in the S over here. So this can hold 2 electrons as well. But notice what else there is. In the second shell, we now have access to P sublevels with the 3 P orbitals in there. So the P sublevel starts at shell 2 and continues and keeps going. So shell 2, 3, 4, 5, 6, 7, so on and so forth. Okay, but it doesn't exist at shell 1. And like I said, there's 3 orientations for P. These are the 3 orientations. If you put them together, they look like this, but there's 3 orientations. So this box together is essentially that, but each of these individually has these orientations here, and each of these can hold 2 electrons in them somewhere. So 2, 2, 2, that's 6 electrons they can hold, and they are degenerate to each other. So if we look at this here, this is our second shell. 2 electrons in the S, 2, 2, 2, total of 8 electrons in the second shell. And this is just a comparison of the two. Here we have our S sublevel, 1 orbital here. And here we have one of the orbitals from the P sublevel, so a P orbital here. You can see the difference in shape, but either way, the middle is the nucleus and there's no electrons there. So you should be able to do questions like this now. If I give you this picture, and I ask you, how do you know this is not shell number 1? This is shell number 2. How do you know this is not shell number 1? Well, shell number 1 only has S. It doesn't have P. P only starts at shell 2, and shell 2 only has S and P. So that's how you would know this is energy level or shell level number 1. Now, that brings us to our next sublevel, the D sublevel. The D sublevel is more complex. These are different orientations that can exist. If you combine them together, it looks like this here. Each of these holds 2 electrons max, so a total of 10 electrons. And the D stands for diffuse here. So this is our third energy level right here. That's where D starts to appear in the third energy level. We have an S, a P, and a D. Don't forget this holds 2. These hold 2 each. So that's 6 plus 2, 8. And this whole thing has 10 because 2, 2, 2, 2, 2, 10. So 10 plus the 8, the third energy level can hold 18. It's a bit different than what you learned in grade 11, grade 10, grade 9, where you're told the rule is 2, 8, 8. Now you can see that in reality, the rule is actually 2, 8, 18. You can actually hold more than 8 electrons in the third shell because you have those D orbitals available to you. So 18 electrons. And when you get into the fourth shell, a new sublevel opens up, and that's the F sublevel with the F orbitals. There's 7 different orientations. Each can hold 2 electrons. So that means there's a total of 14 electrons in them. So you have 7 orbitals in your sublevel, in your F sublevel. And it starts at shell 4 and then continues from there. So this is the 4th shell over here. I know that because I have S, P, D, but also F. And so if you want to know the number of electrons total, you could do 2 plus 6, that's 8, plus 10, that's 18, plus 14, that's 32. So in the 4th shell, you could have a maximum of 32 electrons in the 4th shell. Now, if you don't want to count like that every time, you could use this formula here to figure out the number of electrons in a shell, 2n squared, where n is the main energy level. So let's say you're in energy level 1, you do 1 squared, which is 1, times 2, which is 2. Second energy level, 2 squared, which is 4, times 2, 8. Third energy level, 3 squared, 9, times 2, 18. Fourth energy level, let's see if we're right, 4 squared, 16, times 2, 32. So this here is a summary of what the atoms look like if you were to represent them using the orbitals. So essentially, we have our first 2 electrons we're going to place are in this S sublevel, the S orbital here, the smaller one. These are the neutrons and protons in the nucleus, no electrons there. So the first 2 electrons closest to the nucleus exist in some small region in this sphere here 90% of the time. Now, when that's filled up, we go into our second shell. So this was our first shell, the S sublevel in the first shell. There's nothing else to add electrons to there, so we go into our second shell, and we start filling in the S sublevel in the second shell, 2s. That's this bigger sphere over here, right here, okay? But once that's full, and we still have electrons in place, now we go into our next sublevel in the second shell, which is the P, 2p. We can place 2 electrons there, 2 electrons here, and then 2 electrons over here. Now, if you have more electrons in place, let's say there's 2 more, we can go into our next shell because we ran out of the P's now, and there's nothing else. So we go into our next shell, which is this bigger sphere over here. This is the S sublevel, S orbital in the third shell. And you can see it's much farther away from the nucleus, but you can put those 2 electrons somewhere in this region as well. And if there were more, then you could open a P sublevel again, and then a D sublevel, and then you can go to the 4th after. But this is essentially representing an atom using the atomic orbitals rather than just the individual dots you would be using in Borethefer diagram. This table is a simple summary of the different sublevels we saw, SPDF, with the number of orbitals, the number of electrons maximum, what their shape is, and when the energy level begins. So at energy level 1, 2, 3, and 4. And what we're going to start to see is our periodic table is actually organized based on these orbitals. So we're going to see a trend in our periodic table that shows that different regions of the periodic table fill up different orbitals. So elements, let's say here and here, are filling up the 1s sublevel orbitals. Then elements over here are filling up the 2s sublevel orbitals. Then as you move this way, the elements start to fill up the 2p sublevel orbitals, and then they're full here. Then you go into the 3, and so on and so forth. And these ones here fill up the d's, and these ones here fill up the f. So we're going to take a look at how to determine which where to place the electrons based on your periodic table. So these over here are called your S block elements because you're filling up your S sublevel orbitals. These over here are called your P block elements because you're filling up your P sublevel orbitals. These are your D block elements because you're filling up your D sublevel orbitals. And these are your F block elements because they're filling up your F sublevel orbitals. So we'll see that in more detail later on, but that's the general idea there. So what have we seen so far? We saw the different shapes of the orbitals and how many electrons they can hold. A simplified way of really viewing this is like this. Let's suppose we're drawing a Borethefer diagram, and this is, again, a simplified way of viewing this. We can't really see it that way, but think of it this way a little bit. So let's say this is our nucleus here. This is our nucleus. I'm going to write out, so this is n is equal to 1, n is equal to 2, n is equal to 3. N is equal to 1, you're placing electrons in just an S sublevel. Okay, and that's it. You have 2, you're done. but n is equal to 2, you're now placing electrons in an s sublevel, and then after that in a p sublevel. There's 3 orbitals for that. Here there's only 1. Here there's only 1. Once this is all full, you're filling electrons and you're going to shell is equal to 3, n is equal to 3. You're first filling out the s. You're first going to fill out some s. Then there's some p. And then I'll show you later on the order in which you fill these out, but then there's also some d orbitals. Lowercase there. 1, 2, 3, 4, 5. And then when that's full, you can continue moving up your shells. So it's almost like the shells that Bohr was talking about are further divided into subshells. So we're saying, like, when you zoom in, there's a little subshell of S here and a little subshell of P here. Again, we can't really think of it exactly like that because we have to think of these as regions of space of probability, not where they're exactly found, because that violates the uncertainty principle, but it's still the general idea behind it. So we're going to take a look in the next video at where these shapes come from and how we can describe these shapes using just numbers that are simpler to keep track of. And those are going to be called our quantum numbers. So our quantum numbers are going to be a set of numbers used to describe the general region of where electrons may be found based on probability rules. Rather than having to draw them out like this every single time or in this complex fashion over here every single time, we can show the general region using a set of coordinates almost like you would have for your address. And that will be in our next video.